In the last session, we discussed about the different types of auxiliary or secondary storage devices, namely magnetic tape and magnetic disk. Also, we have known about their intrinsic features, about how they operate and how they work. Now let us move on to the other types of memory which are used in specific applications that may reduce time taken for processing. One of its kind is called associative memory. The associative memory is also called content addressable memory. Let us see why we have to go in for using associative memory. Before that, let us have a quick idea of how we store data, and whenever we go for any searching operation, how does it take place? For example, whenever you want to search a data element, what we generally do, we store them in consecutive storage locations. For example, you make use of an array. Let me call the name of the array as X, and it stores, let me say, around 100 elements, X of 0, X of 1, etc., up to X of 99. So 0 to 99, there will be 100 elements. X of 0 gives you the first element, X of 1 gives you the second element, X of I gives you the I plus 1th element, and X of 100 denotes, X of 99 denotes the 100th element. How do we do searching? Generally, if it is going to be a sequential search, you start from the first location, compare the content in that location with your key register content or your search register content. If both are matching or not, if there is no match, proceed to the next location, and so on and so forth. That means you carry out your searching algorithm in a sequential fashion. That's a linear search algorithm. Of course, to improve the performance, you can make use of a different searching algorithm like binary search. You would have studied in data structure, where you divide your, let me say, the list into an array is a list, or you can say an array is a sequence of elements. It can be called as a sequential list. You can divide your array into two parts and then perform searching either in the bottom half or at the top half. So that is the basic idea behind your binary search. And whenever your array elements are going to be large in numbers, if it is going to be, say, of the order of thousands of elements, in that case, binary search may be fruitful, maybe better. It will be better than your linear search algorithm. Of course, you have binary search tree algorithms. There are binary tree search algorithms. There are many more algorithms available. Let me not get into it. You can refer to the concept of data structures you have learned or you are going to learn, and then you can see how it could be applied in a programming language like C or C++. We normally call this as a table lookup procedure. Whenever you want to search for an element, we look into a table and we wanted to find out its content. The table, what I mean here, is referred as your array, a sequence of storage locations. Let me give you one more example of searching. Whenever you want to go for searching, example in microprocessor, we have got an assembler called a two-pass assembler. In the first pass, it will, whenever you write your microprocessor program, we make use of labels. Whenever you go for a forward reference, the memory address may not be known. The memory address is indicated by the label. Therefore, what we do, we create a table where we record all the forward references and the corresponding label. This is done during the first pass. During the second pass, we have to replace all the memory labeled references with the corresponding memory address. This is what we call them as a table lookup procedure. And in this type of example, we can go for using a different type of strategy, and that strategy is referred as your content addressable memory. What is the difference between the two? Let you take up your generic phenomena of how do we do data storage and then do searching operation or comparison operation. What we do, we have got memory address and then we store data or data item in each and every memory address. So to make it very specific, we identify a storage location only by the address, and the content is obtained from that particular address. For example, ampersand X of 0 gives you the address of the storage, and X of 0 gives you the content of the storage. You know pretty well, memory addresses are denoted in hexadecimal. Okay, let me come to the point. We have an address which is represented in hexadecimal, and then we have the content. To be very specific and in a nutshell, each and every memory address is denoted by the memory address. Using the address, we search and then we get the content. So use the address, go to the location, get the content of the location, then perform comparison. That is what we call them a searching operation. How long are you going to do until the match is found? Sometimes the value you are looking for or the data you are looking for may be stored only once or more than once. Therefore, you stop once you come across the first occurrence, or you can still proceed till the end of your array or till the end of your list is reached. This is basically we normally call it as your storage part of it, where all the elements are stored in a sequential location. When means what I mean here, if the first element is stored, if the first address is going to be 1000 in hexadecimal, that is it's a 16-bit. Each and every hexadecimal digit is equivalent to 4 bits. If I say 1000, it is equivalent to let me say, for example, 16 binary digits or 16 bits. The next memory address will be 1001. The next memory address will be 1002. That means all the data elements will be stored in continuous, or let me say in continuous memory locations, one after the other. This is what we call them as a contiguous storage. And memory is continuously allotted, especially for array types, or for example, list data types in the case of Python. So let me stop there. This is a convention where we identify a storage location with this address. Using the address bus is meant for carrying the address, and that facilitates identifying the storage location. Once the storage location is identified and selected, then you can perform the requisite operation, namely either reading operation or writing operation, depending on the control signal. So let me stop there. This is a general convention. But when you come to content addressable memory, we don't identify the location by the address. We identify them with their contents. That is why it is called the content addressable memory. What is the specialty of content addressable memory? Whenever you go in for searching, how do we generally do? We identify we go by the address and then get the content of that address and then make the comparison, which will be a time-consuming process. And moreover, we do it in a sequential fashion of searching process. But now I want to do it everything in a parallel manner. You know what is parallel processing? Instead of searching the content of only one memory location, I want to compare the content of each and every location simultaneously. Assume I have got M storage locations. I want a content to be compared. The content is available in a, let me say, a key register, just for example. In the key register, I am going to store the content to be compared. Assume there are M words, and word 1, word 2, word 3, word 4, etc. up to word M. We don't identify each location by their address, only by their content. Simultaneously, I will compare the content of the key register with the content available in word 1 separately, word 2 separately, word 3, word 4, etc. up to word M simultaneously. And finally, whenever there is a match, the output will be 1. And whenever there is no match, the output will be 0. So this is stored in a register. We normally call it as a match register. Let us see it to the architecture point of it bit later. Block diagram part of it bit later. The idea is, whenever you have got huge number of data, sequential search will not be feasible. We have to perform searching in a parallel manner, number 1. Number 2, we should not identify the location by their address, but by their contents. In this case, we come across a new type of memory or a new set of memory, and that memory is called associative memory, or it is also called the content addressable memory. So remember, whenever you want to perform searching process with huge amount of data, where parallel processing has to take place, number 1. And number 2, we don't identify by the address, but rather by its content. This is where associative memory steps in, and this is where it comes to picture. And we perform parallel processing. So this is the basic idea behind it. Let us see the hardware organization behind your associative memory.